geometry doesn't perfectly add up as it would add up in the perfect Prussian blue. Plus, we have 6 of these coordinated water molecules. So, and this is really, covalently bound water molecules to these atoms in the structure. It's not the zeolitic water or interstitial water that would sit in these open framework sites that we discussed before. So both these things are possible in this material. Yeah, and if you guys want to read more about this, I send out this paper by B. Wang, which is really a nice review discussing all these kind of things. But I think now we can jump back into the Natron slides, unless you guys have questions on that.
Yeah, thanks. This slide was very good for clarifying. I just have a quick question.
Yeah.
If, say, like 25% of the sites are vacant, do you know if the stability of the structure changes much?
I think in this case, if you think about it, you actually need this defect. That's also described in this paper. So this structure that they sketched up here on the left-hand side, it would actually not check out in terms of the oxidation states, because these cyano groups are typically -1, and then you have Fe2 plus and Fe3 plus. So, this is -6, but you end up with then still a -1 overall oxidation state. So the way this is drawn here, it would not be neutral. You would actually have to have potassium or sodium intercalated here. But this is a stable structure, number B, because the iron oxidation states and the cyano group oxidation state, they perfectly check out to be neutral, which is why this is, a naturally occurring pigment molecule, this Prussian blue pigment over here. So I think this is a pretty stable structure, actually. And in a battery material, you, of course, don't want to have these coordinated water molecules. So you want to synthesize it in a way that, you have charge compensating irons in all these sites. But I believe it would be stable in the B configuration.
Okay, thanks.
Okay, so just very quickly. So the Natron energy cell we discussed, 1.6 volts in their second generation cell, 2 Prussian blue analogs on anode and cathode. And we already looked at the cathode. We noticed that they replaced copper by manganese. And of course, Jeff is right. I mean, this incredibly cheap value of $4 per ton would be for manganese, or the manganese metal is more like on the order of maybe $1 per kilogram, roughly speaking. So it's still cheaper than copper. And that's, I believe, why they replaced this. And they used iron 2 plus 3 plus redox of the iron that is bound to the carbon atoms, which gives you about 80 milliamp hours per gram. So now let's talk about the anode. This is something we did not discuss yet. So first of all, it's a beautiful structure, in my opinion, which you can see here on the right-hand side. Truly cubic crystals, right? And so this anode that they are using in their second generation cell is exactly the same composition as the anode in the first generation cell. So it's a sodium, magnesium, hexocyanomanganate material. So sodium, Mn, Mn, CN6. And it's also made in an aqueous synthesis, so a very cheap process using low-cost materials. We get, about 1 to 5 micrometers primary crystals here, which agglomerate in these larger structures. And in general, they can, synthesize quite a variety of conditions here. Again, this is our general formula, which I think we understand quite good by now, where, this X value denotes the intercalated sodium in the material, can be between 1.2 and 2. Then we have a manganese coordinated to the nitrogen, another manganese coordinated to the carbon. And this X is, again, this stoichiometry factor by which, you know, the two manganese differ. So if it's 1, then they are exactly the same, but it can also be a little deficient in this hexocyano group manganese. And then we fill this up with either, well, we would fill it up with coordinated water, but this N can also be larger than just what comes from the coordinated water, because we always can have in these materials this zeolitic water. So now there is one important difference to the first generation cell. So in their second generation cell, they actually use the manganese 2+, 1+ redox of the manganese atom that is bound to the carbon, so the cyano group. And the cool thing is that this cycles at a voltage of about 2 volts versus sodium. You can see this in the voltage profile down here. So this is just this anode material versus a sodium metal. So that's why we get this potential here. And you see, you know, from about 2.2 volts to 1.8 volts. So an average voltage of about 2 volts, you can reversibly cycle about 70 milliamp hours per grams worth of sodium. And the way you do this is written in this equation here. So you start off with your sodium manganese hexocyanoferrate material. They leave out the water here for clarity. And then you add, you know, N sodium atoms to your structure. So you end up with NaX plus N. And electrons flow, you know, in the external circuit. And then in order to compensate for this charge that you put in the structure, the manganese, which is initially in the 2+ state, which is bound to the carbon atoms, reduces its oxidation state to manganese 1 CN6. So you end up with a mix of manganese that is still remaining in the 2+ oxidation state, and some manganese, I mean, in fact, N worth of manganese, which changes its oxidation state to 1. So this was a pretty big deal because this low voltage redox activity of these low cost Prussian blue analog materials, they were not really well documented in literature. They published this article on that, monovalent manganese-based anodes and co-solvent electrolyte for stable, low cost, high rate sodium-ion batteries. So the reason why this is nice is this low voltage manganese redox gives you more energy than the high voltage manganese 2+, 3+ redox of the generation 1 cell, because the energy of the cell ultimately is, of course, the capacity times the average voltage. So, and I think this becomes very clear if we look at the next chart that they provided, which is really nice because this is kind of a summary now. So we have the anode, which is our sodium manganese CN6 material, and the cathode, which is our sodium manganese iron CN6 material. So now they draw the voltage profiles of anode and cathode versus sodium metal potential. And on the x-axis, we see the capacity. So maybe let's start with the cathode first. So this is from last class, we saw that, you know, this material has basically 3 possible redox couples that you can access. So there's a high voltage redox couple, which is manganese 2+, 3+, which is coordinated to the nitrogen. That's this manganese here, so it can change its oxidation state between 2+ and 3+. Then there's kind of this intermediate voltage redox couple that they are using, so the iron 2+, 3+. And then you can also have iron, which is coordinated to the nitrogen in the structure. You might remember it was written in a little bit of a different way, where you had actually 80% manganese here and 20% iron that was coordinated to the nitrogen. It would be better to write it this way. Sorry, I should have written it this way. And then you have iron, which is coordinated to the carbon. So this 20% iron, which is coordinated to nitrogen, can also be redox active, but they only use the Fe, which is coordinated to carbon. And then the anode has multiple redox couples, as you can see here. And we just mentioned the manganese 2+, 1+, CN6 redox couple, which they use in their generation 2 cell. And then you see it's a nice cell which has the anode operating at around 2 volts versus sodium, the cathode operating around 3.6 volts or so versus sodium. So it's a 1.6 volt cell, and it gives you about 70 milliamp hours per grams of capacity. In comparison to that, the Gen 1 cell used the manganese 2+, 3+ redox couple, which is at a fairly higher voltage, maybe around 2.6 or so. So it only gives you 1 volt cell voltage. Now, why didn't they do this all the way from the start? And the reason is we can plot these potentials also versus the standard hydrogen electrode, which is very useful because the Purbay diagrams are typically written in that way, that you report the voltages versus the standard hydrogen electrode. So this is a simple conversion from voltage versus sodium. You can convert to voltage versus lithium, or you can convert to voltage versus any reference electrode, really. So for sodium, it turns out that the difference is about 2.7 volts between sodium potential and standard hydrogen electrode. So if we convert those voltages, then the cathode would sit at about 0.9 volts versus SHE. And this low voltage manganese anode sits at about minus 0.7 volts. So what does that mean? Jeff already introduced these Purbay diagrams, right? So you have the voltage versus SHE, and on the x-axis you see the pH. So now if we just assume we sit at a neutral pH, we would be at around pH 7. Then you have a certain stability window for your aqueous electrolyte. If you go above about 1 volts or so, you start to see oxygen evolution from water oxidation. If you go below about 0.4 volts maybe versus SHE, you start to reduce your water and you get hydrogen evolution. So we want to stay within the stability window. So, and the blue Fe2+, 3+ redox at about 0.9 volts, it's kind of right at the border where you can be if your electrolyte is not too basic. So this is still okay, but going higher would be really problematic to accessing this manganese 2+, 3+. But the low voltage manganese 2+, 1+ redox minus 0.7, this is definitely below the stability window of water. So how do they do this? We already gave the answer away last time. So basically what they do is they use non-aqueous electrolyte. So I don't know which electrolyte it is. I think Ron mentioned acetonitrile. But at the end of the day, it's an organic electrolyte. They just say it's non-flammable, non-corrosive, and contains sodium ion salt. And that makes this cell really, a regular sodium ion cell, I would say. It's not anymore an aqueous cell. So, you basically make all your electrodes in the usual processes and build your cell in the usual way. So, yeah.
Can you just go back to that slide? I'd just like to talk to the class for a minute about these voltage curves for a moment.
Yeah, absolutely.
Could you take your laser and put it on the low voltage plateau of the anode? Yeah, there we go. Just sort of slide it back and forth across that line. Yeah, there we go. So, folks, when you look at that, do you think the mean field theory would fit that curve fairly well? And the answer is yes. And why would it work fairly well? What's the sodium-sodium distance in this stuff? Does anybody know? based on the structural parameters Michael gave us before?
It is very large, so the repulsive interaction is very small.
Right. It's about 5 angstroms between sodiums, roughly. Okay, then how do we interpret this big step where Michael's going up? He's going to move his mouse up that big step. How do you interpret that step based on the lattice gas models? What would you do there? It's not due to sodium ordering. So what causes this large step based on the models we talked about earlier?
Are we going for more than one sodium in the interstitial site?
No, there's only one sodium per site. It's a change in the site energy. So when you are oxidizing the cation in a different way, the E0 is a different value. You know, so these are actually quite cool curves. All right, sorry to interrupt. I just thought that would be kind of useful to speak about briefly.
Yeah, that was great. Good to put this in context with what we learned before. Cool. Okay, let's spend a couple minutes, really that won't take long, to talk about their technology and their production cell. So it has an organic electrolyte. They make their electrodes in the usual process that we kind of already learned here in class. So they make a, slurry casting, drying, calandering, and then they cut it up and put it into these kind of pouch cells. And something I already mentioned, which is really neat for their technology, since the organic electrolyte the electrodes rather operate in the stability window of the organic electrolyte. I mean, even in the first cycle, the Coulombic efficiency is already 99.9 or greater. So there's no passivating reaction happening at the electrodes. No SEI formation is necessary to make these electrodes work in these voltage ranges. So that's a good thing. It saves cost and is good for electrode kinetics. So, and the real selling point of their battery is, I mean, first of all, it's fairly cheap. And secondly, if you look at these profiles down here, on the left side, you see the discharge. On the right side, you see the charge. They can cycle this battery incredibly fast. So at 20 C, which is about 3 minutes for a discharge, they still get out almost 80% of the capacity. Which color is that? That's the blue line. And then they can also discharge it up to 60 C, which is really crazy. I mean, it's less than 30 or about 33 seconds. I mean, of course, they only get half the energy roughly, but these materials are incredibly rate capable. And that's how you can generate high power in your discharge. And they can also be fast charged in, about 4 minutes or so at C/20. So you have like 3 minutes for the constant current step, and then maybe another minute in this voltage hold here for the red curve, which is 20 C. Sorry, I might have said C/20, of course, 20 C to recharge, the complete battery, 0 to 99%. And then how about cycle life of this production cell? So one positive aspect of these batteries with a really high rate capability is you can get a lot of cycles in a fairly short time. So they cycle their battery at 12 C, charge and discharge, over the full voltage range, which allows them to access 75% of the capacity. They don't need any cooling in their cell. I mean, at these high rates where you have quite a high current flow, the cell heats up to about 40 degrees C, but not more. And you have then only 6% capacity fade. So it goes from a normalized capacity of 100 to about 94 in 25,000 cycles. And these are 2 cells shown here. So that's quite incredible cycle life. The good thing is it only takes them about half a year to run a test like that, because if you charge at 12C, a charge only takes 1/12 of an hour maximum. You can multiply this by 2, so it's only 10 minutes for a nominal 100% capacity cycle. So this testing takes about half a year. The cycle life is quite incredible. And so how does it compare to lithium ion? So the resistance in these cells, which is measured by impedance spectroscopy, we also heard this in class, is quite a bit lower than in other lithium ion cells. So this table shows an NMC graphite cell, an LFP graphite cell, and the Natron energy cell here. So we see in the specs, you know, the average voltage, the capacity, the product of these two gives you the energy of the cell. So we see, you know, the energy of the NMC graphite cell is highest, then we have the LFP cell, and for these Natron cells, due to this low operating voltage, we pay quite an energy penalty, but the cell resistance measured here by impedance spectroscopy at a certain frequency is, you know, factor 10, factor 6 roughly lower than NMC and LFP cells. So we already saw, you know, you can charge these cells or discharge these cells with a really high current, a really high C rate. And then they plot this metric here, max power per energy. So it's the watts of power you get per watt hours of energy in the cell. And here we can see that the Natron cell really stands out, even compared to an LFP cell. So they don't attempt to compete with lithium ion. I mean, they just can't reach the energy density. And also lithium ion, you know, is getting cheaper and cheaper. Here they write, you know, about $80 per kilowatt hour, maybe at some point. But, you know, their value proposition is really that these cells are incredibly safe. They provide a very long cycle life and high power. And, you know, one application of this would be, for example, to put them in server racks. That's, I think, something that they are looking into, you know, as a stationary cell to provide uninterrupted power in case of power outages. But this is a really interesting slide, which shows some future opportunities of these Prussian blue-based batteries that we now learned a bit about. So one thing, I don't know, someone mentioned this, maybe Divya or Aaron, is this multi-electron transfer to cathodes, right? So we were always just looking at, you know, one redox couple, which was active in either anode or cathode. And, you know, we had about 70 milliampere hours per gram specific capacity out of these materials. But you could really achieve something on the order of 140 milliampere hours per gram if you could have 2 electrons per formula unit or 2 sodiums, you know, inserted here per formula unit. But of course, that would require that you have 2 redox active centers that change their oxidation state by 1. So it can be done in something like manganese iron. It could not be done, for example, in nickel. I think nickel would always stay at 2+ oxidation state. Also in the iron hexocyanoferrate material, you can do this, but it is not well documented in literature what happens at this full oxidation of the material, whether it's still stable or not. And, you know, there are no credible reports of practical service life. For sure, Natron is working on this. So that's a very interesting avenue to increase the specific capacity of these materials. Then the other thing, we learned that cell voltage is really very important in these cells because you don't have a large operating voltage, you know, a large voltage difference between anode and cathode in most cases. But what would be really nice is if you could access this even lower voltage manganese 2+1+ redox that is associated with the manganese that is bound to the nitrogen. So we talked about the manganese 2+1+ redox of the manganese that is bound to the CN6 groups. So, and that would be at a lower voltage, and in this cathode that Natron already uses, the question is, can you cycle this reversibly if you have the right electrolyte and all these things? I believe the chromium hexocyanate material is redox active at fairly low voltages. But also, you know, the stability is not very well documented of these materials when you go to such low voltage redox couples. And then one other thing you could do, of course, with these type of materials is you can pair them with a carbonaceous anode. So for example, a hard carbon anode, which is often used for sodium ion systems. And then you would get something around 3 volts for the cell voltage. Apparently this has been tried by Sharp to use basically such a cathode as we see in the first row here, which, you know, would cycle 2 electrons per formula unit. And then you had a fairly large capacity, fairly high operating voltage cell, but it was abandoned. And there are still, you know, challenges. So we talked about this, either interstitial water or covalently bond water in the Prussian blue structure, which you want to get rid of if you want to use it as a battery material. You know, if you have something like this, then also, you know, if you go to very low voltages, I think we discussed this in last class also, the presence of water can be problematic. And then lastly, you know, it's unclear if something like that would really result in a competitive product, but I think it's an interesting avenue for research. And yeah, I think we'll see where Latron ends up with, you know, what they currently already have as their production cell and what they probably come up with in the future. So we can maybe do some questions if you guys have some, and otherwise that's, I think, the material that I wanted to share.
I'd like to make a comment on the previous slide just for a brief minute.
Mm-hmm.
Yeah. So nowhere has anyone talked about volumetric capacity or volumetric energy density of this stuff. And I just want to share a rule of thumb that I have with everybody. So if you think about lithium cobalt oxide, it has the lithium that goes in and out. It has the cobalt, which needs to be there to change its oxidation state. And then it has 2 other atoms, 2 oxygens that are there for the structural part. So the 2 oxygens really are junk atoms that create volume, but they're not really needed for the operation. If you think about LiFePO4, it has the lithium and the iron, and then it has 5 junk atoms. And the volumetric capacity of lithium iron phosphate is pretty terrible compared to lithium cobalt oxide. Now, if you look at this stuff, and if you take the compound in the middle set of rows, which is easy to look at, you have 1 sodium that's going to go in and out, 1 manganese involved in the redox, and then you have, count them, 13 junk atoms. 13. So this stuff is going to have a terrible volumetric capacity and hence a terrible volumetric energy density, just with simple rules like that.
Right.
I think
I've got a question. So you've shown the cycle life of these batteries, and then you talked about the application, which sounds like it's not going to really come close to the amount of cycles that it needs, like that it's capable of. So I was wondering what the calendar life for these batteries would be like.
Oh, I don't know that, to be honest, Aaron, but you know, I don't expect that there would be many side reactions happening over time, even at higher temperatures at the electrodes, because, you know, they are pretty well within the stability of organic electrolytes. So, but I don't have any numbers on calendar life of these cells. But I also agree with you. I found that use case. I mean, yeah, it is what it is. I think it's not easy also to market a new battery technology. You need kind of a launch pad use case. But it's true, right? I mean, you wouldn't end up with a lot of cycles in such a data center application, I guess. but I guess safety and low cost and high rate capability is something that is well suited for such an application.
Yeah, I agree. Thanks.
Okay, I think in view of the time, we should move on to Chong-Yin. And thank you very much, Michael, for that section of the lecture.
Yeah, my pleasure.
Chong-Yin can share his screen and begin his portion.
Hi, everyone. Hello.
Hello,
Chong-Yin.
you're there. We hear you.
Okay. Okay.
So on my end, the audio seems to be a bit problematic. I don't know if you guys can hear Chong.
Chong-Yin at all right now.
Oh.
Still don't hear Chong-Yin. Still don't hear Chong-Yin.
I wonder if Chong-Yin is just the volume level is lower and just your background is louder, and that's why it's cutting off Chong-Yin. So if you turn off your mic, maybe it helps.
Okay.
Still don't hear Chong-Yin.
Is it now?
Not good.
Okay. Sorry about that. How about now? That's fine.
Still not good for me. I don't know about others.
Okay, let me.
Ron coming through loud and clear. He could comment.
No, I can't. Yeah, it's cutting off Chong-Yin for some reason.
I think he's going to sign back in again.
Hello, what about now?
I hear you there.
Okay, I changed the computer. Sorry about that. Okay, let me find.
Seems much better.
Okay, let me find my.
Okay, that's looking good.
Sorry about that. So I just want to present some my understanding of the aqueous electrolyte lithium battery based on my recent 5 years work on that. So I cannot guarantee everything I'm talking right now is 100% true, but yeah. So please interrupt me anytime when you have any questions. Okay, so let's start from this hybrid aqueous battery. From Dr. Chen's lab. So this technology, personally, I don't think it's have a huge difference from Jeff's work like decades ago. So they're still using LMO as a cathode. But the thing is, they changed to the zinc metal anode, which is good because everybody likes zinc in the aqueous system because zinc naturally has a very good potential to have the passivation in the aqueous system. But the thing is, they try to accommodate this LMO cathode, so they're using a very low pH value electrolyte, which is not actually a very smart idea to run the zinc metal anode here. So normally zinc is stable in a high pH value aqueous solution because it will form a very good passivation, zinc oxide passivation. But in the acidic aqueous electrolyte, zinc here, I can guarantee you it will constantly generate hydrogen gas in the battery. So it's not actually not a very good battery here. And even though, so one thing I need to mention is they call it full cell, but I don't think it's really a full cell because they just put a big chunk of zinc metal as an anode in that. So in theory, it's just a half cell of the LMO, and they use the zinc as a reference and counter electrode. And even though they can manage to fix the electrolyte problem, so which means they can even use zinc-free anode here, but still this battery is a hybrid battery, right? So they use lithium chemistry in the cathode and the zinc chemistry in the anode, which means the whole energy density will highly depending on the electron amount, which will largely reduce the energy density of the full cell in the real scale-up batteries. Okay, so that's pretty much every research proposed aqueous battery before we successfully extend the electrochemical window of the aqueous batteries. So that leaves the next part. So for this, we call so-called water insult electrolyte. It's actually the idea is very simple. It's just using some lithium salt with extremely high solubility in the water and forming a high concentrated aqueous electrolyte. So the work is actually initiated by Dr. Storer, which is a colleague of mine. And why the story is he did some high concentration LTFSI salt in DME electrolyte back during his PhD study for lithium sulfur battery, which works extremely well, especially for the lithium metal anode. So when he came to Maryland, we have this huge ARPA-E aqueous battery program. So I think the natural instinct for him is just try the same salt in the aqueous system. So surprisingly, it's even getting like 21 molar TFSI concentration. It's molal, which means it's a molar per kg. It's we actually putting too much salt in it, actually changing the density of the whole electrolyte. So we can only use the molar per kg, which is ancient units decades ago. So the first work he published on this science paper is just to use a single salt 21 molar TFSI, and he ran the battery with LMO as cathode, moly sulfide as anode, which this battery can charge to 2.3 volt. And the whole electrode window of this electrolyte is actually extended to like around 2.9 volt. So after that, he also find you can even put more salt in this system. Another salt is LiOTF, and you can put 6 more molal salt in this system and forming the 28 molar high concentrated electrolyte. And the window is slightly extended to more than 3.3 volts. And the whole battery he using here in this paper is cathode is LMO versus titanium oxide. So the battery actually being charged to 2.5 volt. And he called it water in bisalt, which has a binary salt in that. So in the same time, I think this Professor Yamada here is actually one reviewer of this science paper. So his group actually, in the same time, find out you can put more, more bigger anion salt in this 21 molar TFSI, and they chose to use this even bigger anion salt and achieve a similar, like 28, 27 molar high concentration electrolyte. And they claim they can run a battery which being charged to 3.4 volts, but I highly doubt that because they actually run the battery at 20 C, which and they can even still cannot get to the 100% current efficiency. But interesting is they actually propose to use high voltage lithium nickel manganese oxide as the cathode and the LTO as the anode, which in theory can provide 3.5 volt voltage, which if this battery runs well, it can deliver the same level of energy density as the non-aqueous electrolyte system. So why these salts are so unique? I think even the lithium FSI can have a huge durability in the water. Is that these three salts has a pretty similar anion structure, but only thing different is for the FSI, the fluoride is forming a sulfur fluoride bond, which is not so stable in the water. So, which means if you put FSI salt in the water, it will forming HF acid. But for the TFSI and the BETI, they forming a fluoride carbon bond, and the whole molecular anion is more stable and it's totally stable in water. And the unique of this salt is its anion is bulky, it's soft, and more importantly, it's the polarization of this whole anion is like well distributed, which means the lithium salt, when it's forming the crystal, the lithium salt has multiple sites to associate, which means this salt is very easy to dissociate in the solvent and very hard to form a very good crystal. That's why this salt is has a huge solubility, especially in the water. So Michael Dean in the Army Research Lab has studied its phase diagram with TFSI, lithium TFSI and the water. As you see, we actually didn't use, they claim it's a hydrate melt, but I don't think it's really a hydrate melt. If it's hydrate melt, we're still using this kind of value here, right, the concentration. But actually we, the 21 molar is here, so we getting the room temperature and the highest solubility, and it's reaching to 0.27 like ratio of the lithium TFSI, which is actually the 21 molar here. So that implies that this whole system is also has another drawback is it don't have a very good thermal stability. If you change the temperature a little bit, it will, I think it will become very unstable for the whole system, especially for the low temperature. But the bizarre thing here is normally we think in the normal electric system, if we reach like 5 molar or 10 molar, it will have a very high viscosity because you have a huge amount of ion pair in this system. But in this water insult, it's very bizarre because if you reach to the higher concentration, according to the Warden plot here, it actually reaching to the superionic area, which means the viscosity and the conductivity is decoupled. And another bizarre thing here is we actually measure the transference number of the whole system. As you see, if as the concentration rising, the cation, which is the lithium ion, the transference number actually increasing and almost reached to like 0.7. And for the 28 molar, I think it's reached to the 0.8, which is very close to the value we test in the solid state electron. And so overall, the ionic conductivity of this 21 molar is acceptable for the lithium battery, which can still getting like 10 millisiemens per centimeter. And the odd thing here is the viscosity is still increasing exponentially, but the ionic conductivity is linear. So I think pretty much prove that the ionic conductivity and the viscosity is decoupled here. And another thing is it reduced the oxygen dissolution solubility in this system. So we don't need to worry about the oxygen for the anode efficiency, as Professor Yao proposed on his paper, I think. So that's the criteria of the conductivity criteria for this electrolyte, which makes it acceptable for the successful lithium battery electrolyte. But the more important thing
wait. Okay, we have to watch the time here.
Okay.
So I think what you should do is take questions up till the previous slide and then pick up here next time.
Okay, sorry. So any questions so far?
Changin, I had a question based on this viscosity versus conductivity plot. So we learned in like class about this Stokes equation is used to like find out these values of like the relation between viscosity and conductivity. So when we are saying like decoupled or like what is really happening, like what is different about these terms? Is it like the Stokes radius, or is it like the size of the particles? I don't know, like what is changing?
I think really changing is normally why the viscosity and the ionic conductivity is associated, because the real charge carrier in the electrolyte, the concentration is pretty stable. Even you changing the concentration, it's not changing so much as the viscosity. So normally in the in some equation, the charge carrier density is actually being fixed as a constant, but actually it's not. It's a variable by the temperature, but it's temperature. It's not affected so much as viscosity by temperature. So but what happens here is actually when you're getting in this system, when you're getting higher concentration, the charge carrier in this system is even higher than the normal. So which means it goes into the superionic system. It's more like ionic liquid. So we normally see this kind of Walden plot in the ionic liquid system. So that's my understanding. So maybe Jeff can comment on that.
Yeah, I can make a comment. You know, the Walden plot looks linear, almost linear, the blue points.
Yeah.
So that implies that the molar conductivity, which is the conductivity divided by the concentration, the vertical axis, is controlled fully by the viscosity and not by any change in dissociation. It looks like the salt is fully dissociated the whole way, which is kind of very cool, even at these very, very high concentrations.
Yeah, we will mention we will talk about this bulk structure later, but yeah, that's a very bizarre thing in the highly concentrated solution.
Yeah, got it. Thanks.
Okay, so if there's no further questions, we'll come back to this on Friday.
Okay, thank you.